Today we're going to be doing some practice problems for section 6.3 on our binomial and geometric random variables, which, good morning, Carly. We were introduced to yesterday in the textbook. Real quick before we get into the activity, do a quick little review here. Let's share my screen. Let's see what happens if we do it this way. Alrighty, so hopefully you guys can see my screen in OneNote. So a couple things to start. Right, in section 6.3, we talked about binomial random variables and geometric random variables. Both of these have unique circumstances attached to them to when we can use them. Right, for binomial random variables, I need that all. And we're just going to call these binomial random variables. Right, we need to have a binomial setting. Right, in order for something to be a binomial random variable, right? And yesterday we saw that this is lovingly referred to as bins, right? This needs to be binary, right? It needs to be independent. There needs to be a set number of trials, and the probability of success must be consistent for each trial. So these are the things that must be true in order for something to be in a binomial setting and then be able to be a binomial random variable, have a binomial distribution, and such, right? Always need to keep these things in mind. Now, obviously, the problems today are in the setting of being either binomial or geometric, so we know that going into it. Right? We also, with our binomial random variables, we can calculate the binomial probabilities. With our binomial probability formula. Right? And that is the probability of x equaling k. So the probability of having k successes in a certain set number of trials, right, is equal to n choose k, where n is the number of trials, right? K is the number of successes we're interested in, times p to the power of number of successes, where p is the probability of success, times 1 minus p, otherwise known as probability of the other outcome, something that we don't consider a success, time to the power of n minus k, number of failures. Right? This will give us probability of having an exact number of successes. Right? If we want the less than or equal to, greater than or equal to, we must use modifications. We can use technology, use the complement rule to then get those probabilities. In a nutshell, those are binomial. The other side of this that we saw yesterday was geometric random variables. All right. For these to be geometric, we still need independence. Right. So each trial, each outcome is independent. Right. And we are interested in the number of trials to get one success. That's the key difference that separates geometric from binomial. We stop the trials once we get our first success. So geometric random variables do not have a set number of trials, but they do have a set end when I get a success. right? We also need the probability of success to be consistent. In textbook, they say that it's fixed. You can use that term as well, right? The geometric probability formula right? In this case, we have the probability of x. We'll use a different letter. We'll say our random variable is y, in this case for geometric, equaling k. Right? Whereas this case, k is representing the number of trials to get one success. Right? We have, if I'm remembering this correctly, I remember the binomial one very well. Check my geometric. Yes, I was right. All right, so you have the probability of failure times, what is this, k minus 1 times the probability of success. Right, and again, k represents the number of trials to get the first success. So that means we have k minus 1 failures. Right? And so the probability of success only gets multiplied once. Again, both of these we can use to calculate probabilities that aren't just equal to a certain outcome. We can do less than or equal to, greater than or equal to, by doing some slight manipulations to the formulas, or by considering the other possible outcomes that make that event true. Right? So this is in a nutshell what we saw yesterday in a brief 5-minute review. Is there any questions before we get started? All right. Excellent. I'm missing people. Oh yeah, I'm missing people. Ooh. All right. So then, stop that one. All right, so I'm going to share the link to our activity for today in the chat. There it is. So this is another Desmos activity. Hopefully you find this helpful. This is for our section 6.3 practice problems in Desmos. So please, if you have not joined the class or joined the activity, please do so. This is for you guys. Practice. Here's the link one more time, just in the event that you missed it. Hopefully you didn't. All right, so we're going to start. And we're still missing a couple people, but the show must go on. So, binomial distribution or not. Right, in the following two example scenarios, you need to determine whether the given random variable has a binomial distribution. We have two scenarios. You need to decide, is it a binomial distribution, right? Is it fitting into our binomial setting, essentially? Or is it not a binomial distribution? Does it fail one of our conditions of bins? All right, so you need to kind of like mentally check these off, or if you need to write on a piece of scratch paper, please do so. And decide, are these binomial settings? Do they have a binomial distribution? Alrighty. So here we go, guys. For the first scenario, example 1 with seed depot, that is a binomial setting. So that does have a binomial distribution. It meets the 4 conditions of bins. It's binary, either the seed grows or it doesn't. It's independent. If one seed grows, has no effect on another seed growing, another one of the 20 seeds, right? There's a specific number, there's 20 randomly selected flower seeds, and there's a probability of success that is consistent, 85%, right? Those four things satisfy bins. That means we have a binomial setting, which means we have a binomial distribution and a binomial random variable. Right? For question number 2, or example number 2, this is not a binomial distribution. Can anyone tell me what fails? What part of bins fails? So I'm going to take a stab at it. What part of bins fails? Anyone? What fails? Why is bins not satisfied?
Because they're not independent.
And why are they not independent? That is correct.
Because
why would they not be?
When you remove one of the names from the hat, it changes the probability of picking of like the rest of the names because there's a different amount of names there.
Correct. We call that sampling without replacement, right? Sampling without replacement is inherently not independent because as you remove options, the probability of that thing happening again reduces or changes. All right. Thank you, Devin. All right. Very good. We're going to move it on to our next example. Elk. Biologists estimate that a baby elk has a 44% chance of surviving to adulthood. Assume this estimate is correct. Suppose researchers choose 7 baby elk at random to monitor. Let X equal the number who survived to adulthood. Use a binomial probability formula to find the probability of 4 elk surviving to adulthood. Please enter your answer in decimal form, not a percent, and round to 3 decimal places. Okay, so you might need some scratch paper for this one, and or a calculator. If you check though, I do have a calculator available right here on the side if you click the little calculator at the top of the question. I can see there's a chunk of you who have answered this and some of you who have not. That's okay. So again, please make sure you're putting your answer in the format requested, right? That's something you do want to take into account when you're answering questions, not only for this class, but for, AP exam and things like that. Answer the way being asked. So on this one, we need to use our binomial probability formula, right? And let's see if I have this, if this is going to work for me the way I want it to. So this is the work, so to say, on this one. All right, we have n equaling 7. There's 7 elk. That's how many trials we had, so to say. Probability of success is 0.44. The K we're interested in, right? The number of successes is 4, right? And our random variable X is the number of elk surviving to adulthood. Probability of X equaling 4 is 7 choose 4, right? That binomial coefficient, times the probability of success to the 4th power, times the probability of failure, 0.56 to the 3rd power. We get about 0.2304. If we round to 3 decimal places, right? 0.230, right? If you're trying to type in the formula here for 7 choose 4, I don't know how to make Desmos do that. So it's going to show up as a fraction. I don't necessarily recommend that. It would be better to just type it in 7 and then type the letter C and then the number 4, and then at least I know that that's what you're meaning. That's how your calculator produces it most of the time too. Out of the 7 elk chosen, there's about a 23% chance of 4 of them to survive to adulthood. So that's our explanation in context. Is there any questions about this problem?
I have a question.
Yes.
Where did you get 0.44 and 0.56?
Very good question. Okay, so in our problem context, right, we have a 44% chance of surviving. So that's 44% chance of success. 44% as a decimal is 0.44, right? And then the 0.56 is 1 minus 0.44, right? So when we're calculating these probabilities here, and we have a probability of success and a probability of failure. Between those two, it needs to add up to 100%, or when we're using decimals, it needs to add up to 1. So if this is 0.44, this has to be 0.56 because 0.56 plus 0.44 is 1. Does that answer your question?
Yes, it does. I'm sorry. Another question.
Sure.
How come? Why did you put the power of 4 and the power of 3?
All right, excellent. So we get the power of 4 and the power of 3 for these because the power of 4 is the number of successes, right? And that goes with the probability of success, right? So those two things go together. Let's see if this will work the way I think it will. Right, so this is that's the number of successes I'm interested in, right? Is 4, right? And this is the probability of success. If I had 4 successes, means I had 3 failures. Right? And this, if I have a 44% chance of succeeding, that means I have a 56% chance of failing. Right? So the exponents on these are directly related to the number of failures and number of successes. Right? And they're also related, so we get number of success as the exponent here. It's also that number in my binomial coefficient, the 4, right? The number of successes plus the number of failures is the number at the top of the binomial coefficient, the 7, right? 4 plus 3 is 7. So all these numbers are connected. They're all coming from like a common source. We just need to know which one goes with which thing. All right. Hopefully that clarifies.
Yes, thank you.
You're welcome. All right. Any other questions before we go to the next problem? All right. Moving on. All right. This is sowing seeds. So we're going back to our seed depot. All right. And we're considering some stuff happening here. So Seed Depot advertises that its new flower seeds have an 85% chance of germinating or growing. Suppose that the company's claim is true. Right, so we can use that 85% as a success probability. Judy gets a packet with 20 randomly selected new flower seeds from Seed Depot and plants them in her garden. Let X equal the number of seeds that germinate. Right, our first question here, find the probability that exactly 17 seeds germinate. So the probability of X equaling 17. The second part of the question here is, if only 12 seeds actually germinate, should Judy be suspicious that the company's claim is not true? You need to compute the probability of X being less than or equal to 12 and use this result to support your answer. And you'll essentially finish this explanation here. So, all right. So here we go. Probability of exactly 17 seeds germinating. It should be 0.243 if you round to 3 decimal places. If you round to 4, 0.2428. Yes. That is correct. Most of the answers I see in here are correct. All right. Make sure. So the one, we got an incorrect response in here, and that is because the binomial coefficient was incorrectly set up. It should be 20, choose 17. We have 20 randomly selected seeds, 20 trials. We're looking for 17 successes. Right, and that should adjust things properly. All right. And then if only 12 seeds actually germinate, should Judy be suspicious that the company's claim is not true? Right, so we compute probability of X being less than or equal to 12 and use this result to support your answer. If you did that math, you should have gotten a probability of 0.0059 or something close to that, which means there's a less than a 1% chance of 12 or fewer seeds germinating purely by chance, which is incredibly small. So Judy should probably be a little bit suspicious of their claim, right? Because that shouldn't happen if their claim is true. It shouldn't really happen that often, at least. I'm not saying that it can't happen, but the odds are against it. Right. Is there anything I can clarify on this example?
How did you get the number for X less than or equal than 12?
Okay, so let's look at, let's see, there it is. So for less than or equal to 12 here, there's a couple ways we can calculate this. So we're going to do it the long way. We would need to find the probability of X equaling 12, add the probability of X being 11, 10, 9, 8, all the way down through 0. And we add those up and we'd get probability of X being less than or equal to 12. The other thing would be to use your graphing calculator and use the binomial CDF calculation or command. And that is right here. So to get to that, we'll go second, vars, which above it says distribution. All right, so this gives us different distribution calculations. We'll go to option B, which is binomial CDF. The binomial PDF gives us equal to amounts. We want less than or equal to, and that is the binomial CDF command. We'll hit enter. I've already entered in the number of trials, the probability of success, and the X value I'm interested in. All right, and in this case, that's the K value we use in our formulas. In this case, K is 12, so this is 20, 0.85, and 12. And we hit enter, and we get 0.00592, blah, 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 blah. Right? So that's the most efficient way to do it. I would recommend, if you're showing your work, right? You're taking the AP test and says, show your work. I would recommend showing something like what I have here. It's clear that I know what this calculation is, but I also know that I don't want to take the time to do this by hand and calculate each one. So I'm going to use the calculator. And I have clearly labeled, I'm using the binom CDF command with an n equal to 20, p of 0.85, in this case k. You could say x value just like it does in the calculator, and that would be fine, equaling 12. That's very low. Right? Is there any other questions? Excellent. That means we're going to move on to the next set of problems. This one has a couple of parts using the same context, so I'm going to actually open up both of those windows, right? Because they're kind of related. So as a special promotion for its 20-ounce bottles of soda, a soft drink company printed a message on the inside of each cap. Some of the caps said, please try again, while others said, you're a winner. The company advertised the promotion with the slogan, 1 in 6 wins a prize. Suppose the company is telling the truth, and that every 20-ounce bottle of soda it fills has a 1 in 6 chance of being a winner. 7 friends each buy one 20-ounce bottle of the soda at a local convenience store. Let X equal the number who win a prize. So first explain why X is a binomial random variable. How do we know it is a binomial setting here that we're dealing with? Then find the mean and standard deviation of X. Round your answer to 3 decimal places, please. And then you're going to interpret each value in context. All right, so once you enter in your numbers here, we'll hit submit and explain. Please say what the mean and standard deviation tell us within this context. Don't just tell me how you calculated it. All right. Excellent. And the next one is same context, but we're trying to find the probability that 3 or more of the 7 friends win a prize. So we're calculating probability of X being greater than or equal to 3. And round that result to 4 decimal places. All right, guys, please take a pause. And we're going to talk about the first part of this 1 in 6 wins problem. All right, so we've already talked about the context. We want to explain why X is a binomial random variable. It is because it passes the conditions for bins. It's binary, you either win or lose. It is independent. Winning with one soda has no bearing of winning or losing on the next soda. There is a specific number of trials, n equals 7. And there is a fixed probability of success in each opening of a soda, which is said to be 1 in 6 or 1/6, about 0.167, 0.167 if you round. So since those conditions are met, we have a binomial setting, so it's a binomial random variable. Right? Mean for this situation is about 1.167, which tells us that in many occurrences of 7 trials, all right, we would expect about 1.167 wins in every 7 trials, right? And our standard deviation is about 0.986. If you got 0.987 or something close to that, it's a rounding error. That should be okay. Your answer, if you rounded the mean, or n times p, to 1.167, used that in your under square root sign, your answer is going to vary just a little bit. If you use the actual fraction of 7/6, your answer will be a little bit more accurate within a decimal place here or there. So don't get too stressed on that. All right. And in context, that means that we would typically expect a variance of about 0.986 from the mean of 1.167 on average. Any questions on this part of the problem?
I do.
Yes, go ahead.
Sorry, I actually have a hard time finding the mean and the standard deviation for that one.
Okay. Let's consult the math. There we go. So in this case, remember with a binomial random variable, we can calculate mean and standard deviation using the rule. Let's see, we have the mean is going to be equal to NP, and our standard deviation is going to be equal to the square root NP times 1 minus P. All right, and this would be for our random variable X, whatever that might be. All right. So we need to clearly identify what is N and what is P. In this scenario, we have an N of 7 and a probability of success of 1/6. Again, if you round that 1/6 to 0.167, you might get a slightly different result than what we have here. Right, so the mean of X is 7, N times P, 1/6. We get 7/6, 1.167. Right. Standard deviation is going to be the square root of N times P times 1 minus P. We have 7/6 times 5/6. Right, that gets us the square root of 35 over 36, which is equal to the square root of 35 divided by 6, or 0.986. It's totally fine if you just start here, put this in your calculator, and get the rest of the stuff. I like doing the math, so I do it because I can. That's just interesting for me to do. Now, as we move on to the next part, this is my suggestion for the second part of this problem on the next page. You want to find probability of X being greater than or equal to 3. It's going to be easier to find 1 minus probability of X being less than or equal to 2. Right? Use the complement rule. If I wanted to calculate P of X being greater than or equal to 3, I'd have to find X equaling 3, X equaling 4, X equaling 5, X equaling 6, add those all up. There's no shortcut on the calculator for that. I can have my calculator do probability of X being less than or equal to 2. Right? Use rules in your favor. Sorry, I went past what you asked, Maria. Did I answer your question?
Yes, you did. Thank you.
Excellent. You're welcome. All right. So then, are there any other questions? So I'm going to suggest that you move on to the next part of the 1 in 6 wins problem, all right, where you're going to calculate the probability of 3 or more of the 7 friends winning a prize. And again, I suggest using the complement rule to save time on the calculation. Right. So we'll move on to this part here. All right, so for this scenario, you should have gotten probability of 0.0958. And again, I used 1 minus the binomial CDF, n equaling 7, p equals 1/6, x value of 2. If you used an x value of 3 on accident, like p of x less than or equal to 3, that's the incorrect calculation. Right? Because 3 is part of what we wanted, not part of what we wanted to subtract. Okay. Any questions about how we can find this solution? All right. So what we're going to do here is we're going to jump to the last question in this chunk because that is a geometric one. We're going to do that as our last thing here. So I'm moving us all to the 9th frame. That is once again dealing with the exact same context for the 1 in 6 wins. Right. Alan decides to use a different strategy. This here. For the 1 in 6 wins game, he keeps buying one 20-ounce bottle of soda at a time until he gets a winner. Find the probability that he buys exactly 5 bottles. Please round your decimal place. Round your answer to 4 decimal places. So we're now going to use the geometric probability formula. All right. With the same information from this problem. We're looking for the probability of our random variable, maybe we can call it y, equaling 5. Alrighty, so here we go. Our last calculation for today, the 1 in 6 wins again. All right, this is now a geometric probability. What's probability that Alan has to buy exactly 5 bottles to get a success? Right, we should end up with a result of 0.0804 if we round properly, so about 8%. And the math behind that, Wiki, where'd it go? Oh, it didn't show up yet. There it is. Right here. So we're going to let y equal the number of bottles to get a winner. Probability of success is 1/6. I'm interested in a k of 5. All right, I want to know how long if it takes 5 bottles. Probability y equaling 5 equals 1 minus p times to the power of k minus 1 times p, which is 1 minus 1/6 to the 5 minus 1 power times 1/6. 5/6 to the 4th times 1/6, and we get 0.0804 rounded to 4 decimal places. There's a few extras in there. All right, so remember, geometric probability does not have the binomial coefficient. There is no 5 choose 2 or 7 choose 5 or anything like that. That's not going on with the geometric probability. The binomial coefficient belongs with the binomial probability. All right, so we get about 8%. So it's got about an 8% chance of getting a winner in the first in 5 bottles. All right. Any questions about this problem?
Where did you get 1/2 4?
1.
1 out of 4. The 1 minus 1 out of 4.
Oh, that's a 6. I'm sorry. It's just me scribbling too
okay.
fast.
Sorry.
No, that's fine. Yeah, that's on me. We'll fix it. Where is it? Yeah, there we go. Sorry. Yeah, sometimes when I write my 6s too fast, they turn into 4s, and that's a problem. Yes. All right. Awesome. Okay, so stop sharing stuff here. That's it for today. Hopefully you guys learned some stuff about our new probability calculations with binomial and geometric. I do still heavily encourage you to look at the practice problems if you need some more practice with this. Also, now is the most excellent time to start the Chapter 6 assessments, the multiple choice and the free response questions. All this stuff is nice and fresh. I would recommend trying to get to those in the next week. All right, so that you can do it while this stuff is still fresh in your head. And if you do have any questions on any of those problems, you need some help or support, please let me know. I'm happy to help.